I'm really excited that today, the virtual nature of today's conference has brought us really a top flight list of international speakers and participants from all over the world. Our first speaker today is Evgeny Feigin of the Higher School of Economics in Moscow. He'll tell us about Veronese embeddings, arc schemes, and global Demazure modules. So I'll pass the word to Evgeny.
Thank you very much. And so I'll share a screen in a minute. So let me do this. And thank you very much for the invitation. It's a special pleasure to talk here. Actually, it's my second time in Montreal. My first visit was a year ago, and it was also the CRM. And so I like the place very much. So I hope to come again once, well, in a year or two someday. So let me apologize from the very beginning. So I'm still not quite comfortable with the Zoom talks. So please ask questions whenever you want to ask. So at any point, because so giving a talk via Zoom is a kind of much more complicated compared to the usual talks. I'll try to do my best, but please ask questions, and I'll be happy to give any comments or clarifications needed. The title of my talk is Veronese embeddings, arc schemes, and global Demazure modules. And I'll try to give all the notions and introduce the objects, the main players. And before I start, let me mention that this is based on the joint work with Ilya Dumanski, and also with there is some collaboration with Michael Finkelberg. But I'm not actually going to talk today about these applications. So I'll try to stay on the kind of concrete footings and then try to go to the more general picture. So let me start. And also, please let me know if some technical problems occur or you can't see something or something like that. So let me start with the initial definitions with the classical picture. So this is going to be very, very classical. So what is the Veronese curve? So we fix a number d. So this is just a natural number. And it's here. And also, so we consider the map from P1 to PD, and the map is very concrete. So we send a pair AB. So this is an element in P1 to an element in PD given by the set of explicit homogeneous coordinates. So you start with A to the D, and then the next one is A to the D minus 1B up to B to the D. And there are exactly D plus 1 coordinates here, which correspond to being a point in the D-dimensional projective space. So explicitly, the homogeneous coordinates are given by A to D minus I, B to the I, and the I, this is the index, runs from 0 to D. Good. So this is our Veronese curve. So you can just see it as a P1, but embedded into different projective spaces. So, well, this is the usual picture where you have a projective variety with several different embeddings. So let's go further. And what are the questions we can ask about this embedding? So we can ask, what are the relations satisfied by the coordinates? And well, you can easily see that the relations are given by the quadratic expressions xi, xj equals xu, xv. And the condition is that I plus j is u plus v. So one easily shows that the expressions of this form satisfy the quadratic relations below. Well, there is something to do to show that no other relations are needed. So meaning that if you have a polynomial vanishing on the Veronese curve, then this polynomial sits inside the ideal generated by the differences of the left and right hand sides. So let me give an example. If these two, so this is the case here, so these two, so meaning that we have three homogeneous coordinates, x0, x1, x2, then those three satisfy the only relation, x0, x2 equals x1 squared, and the claim is that the ideal generated by this single polynomial gives the vanishing ideal for this Veronese curve. And for d equals 3, you have now three relations. They're written down in the line below, and you can see the form of these relations. So this can be restated in a more kind of scientific way, saying that this ID gives reduced scheme structure for the Veronese curve CD. But this is just a fancy way of saying that the ideal of relations, so all the polynomials vanishing on the Veronese curve on CD is generated by this set of quadratic polynomials.
Could I just make a little comment?
Yes.
It's also the Tucker map from the Grassmannian of two planes in N into this Fourier space.
Absolutely. Yes. Yes, that's right. That's right. So actually, indeed, so this Tucker embedding is important for us. So we'll see a bit later that the group acting here, for example, here it's SL2, does play a crucial role. And so this can be seen already here. Okay, so let's go further. So let me once again, this is my request to ask and to react as much as possible. So I mean, it's much easier than to kind of have a contact with people. Okay, so let me make a link to the representation theory. Actually, the Lie group and Lie algebra, which is important here, is SL2. And what's the reason for that? So let us do first, let us make one statement. So let V and omega be n+1 dimensional irreducible SL2 representation. So, well, this is very standard thing. And so we want somehow to describe the coordinate ring, the homogeneous coordinate ring, which is given here. So this is the quotient of the polynomial ring in our variables by the ideal of relations using the representation theory of SL2. So the reason to expect that the SL2 must play a role here is that the projective line P1 is acted by SL2, and actually this is a flag variety for G mod B. But let me state the answer, and then we'll get to this action of SL2. So the claim is that this quotient, the homogeneous coordinate ring, is isomorphic to direct sum of all the SL2 modules such that the highest weight is divisible by d. So you remember this d is the degree of the Veronese curve. For example, for d equals 2, so what we get is the direct sum of even representations. So this is given here. And of course, if d is 1, then R is just, so R is simply C of x0, x1. And if you take homogeneous polynomials of degree n in two variables, then what you get is nothing but irreducible n+1 dimensional representation of SL2. This is trivial case, but already d equals 2 case is not that trivial. So why does the group play a role? And the reason is that the projective space where our Veronese curve lives is PD, and let us realize it as the projective space of d omega. So remember that v d omega is d+1 dimensional, so this indeed the d-dimensional projective space. And then since v d omega is SL2 module, then the group SL2 acts on the projective space. And actually we can realize our Veronese curve in a very concrete way. So we have a high state vector here, and then we can consider the line corresponding to this high state vector. So it's given here, and then just take the SL2 orbit inside this projective space. So in other words, we have this map from P1 to P of v d omega. And well, this map is SL2 equivariant. So there is an SL2 action here and SL2 action here. And this is equivariant map. And well, the corresponding curve is just the orbit of one point. So this is the classical picture. And so what we are going to do, we are going to somehow make the life much more complicated. And what is the way is to somehow make infinite number of variables out of a finite number. And here is the picture. So this is called arcs, sometimes called arc schemes. And actually, there are many reasons why one should be interested in such picture. So probably the first person to study this was John Nash. Well, he was doing some differential geometry, and actually he was thinking about some variety, and then arcs in this variety. So meaning that you somehow consider, instead of considering just a point, so this is a variety. I don't know how should I draw it. And then inside this variety have an arc. So this arc is parameterized by a parameter t. And then instead of considering just points of the variety, you consider arcs. And then you want to somehow understand the structure of this arc variety. But of course, this has been done much more algebraic afterwards. So let me formulate the version we need. Oops. So what do we need? So we consider our d+1 variables, x0 up to xd. And now instead of working with this finite number of variables, let us introduce infinite number of variables, and they are given here. So the lower index I corresponds to the number, the indexes of the initial variables. So I goes from 0 to d. And then we have also the upper index. This upper index is k, and it runs from 0 to infinity. So this is our k. So we pack all the variables, all the new variables, into generating functions. So you can see that these generating functions are written down here. And actually, so they are given in a very explicit way. So these are series. Well, you just start with the xi 0. So plus t times xi1 plus t squared xi2 plus so on. So this is an infinite series. And you can see that the lower index is fixed and the upper index runs from 0 to infinity. And then you have this infinite expression given here. So okay, so these are our variables. And now what do we want to consider? So, so let's do the following. So we consider the ideal. So now, of course, we're going to be interested in the ideal ID introduced above. But let's first start with an arbitrary ideal I in the polynomial ring infinite number of variables. And let us replace each variable xi with a generating function xit. And then we expand. So what's happening? So we have some polynomial p in our variables x0 up to xd. And then we somehow introduce a new polynomial. So now instead of taking just a variable, we put x0 of t, xd of t. So now this is a polynomial in our variables x, I, k, and also a variable t. And then we expand in t. So meaning that now the coefficient in front of each power of t is a polynomial in this polynomial ring in infinite number of variables. So you can see that if you are given an initial ideal I, then after this procedure, you get an ideal, which is denoted by j infinity of I, inside the polynomial ring in infinite number of variables. So these variables x, lower I, upper k. Okay, so this is somehow the general construction. Let me give you a few examples so you can feel how does it work. So the first example, which I call here baby example, but maybe it's not a good word because actually this example is an important one. So this comes from the affine Kac-Moody algebras theory, also important in the vertex operator algebras theory, although the example looks quite simple. So we consider polynomial ring in one single variable c of x, and this is as simple as possible, so generated just by x squared, so nothing else. So this is a very simple ideal. And now we take our generating function x of t, and you can see that the series consists of terms where our single variable x got kind of made it starting from this 1x, we get infinite number of x's, x0, x1, x2, and so on. And what is our J infinity of I? So this is now an ideal inside the polynomial ring in this infinite number of variables. And what we have to do, so our recipe is to start with the x of t squared. So this is just the square of the generating function. We expand it, and what do we get? So the coefficient in front of the t to the 0 is just x0 squared. The coefficient in front of t to the 1 is x0, x1. Well, there is a 2 there also, but doesn't matter here. And then the coefficient in front of t squared and so on. So it means that our ideal, our arc ideal is generated by these polynomials. So now this is infinite number of polynomials here, and this ring, I mean the ring, the quotient ring C of x upper 0, x upper 1, etc. Modulo this J infinity of I. So this somehow describes the structure of basic or vacuum representation of the SL2 hat, a fine Lie algebra attached to SL2 of level 1. So, okay, let's go further with another example. So let us consider the case of the Veronese curve of degree 2. So D is 2 here. And then we know that I2 is the ideal generating by a single binomial x0, x2 minus x1 squared. And what is the recipe? So instead of considering this monomial with binomial, we consider the series. So this is x0, xt times just the product of x0, xt minus x1 squared of t. So this is the series in t. So our recipe says that we have to expand it, and the expansion gives us infinite number of coefficients. So for example, this guy is a coefficient in front of t to the 0, and this guy is a coefficient in front of t to the 1, then t to the 2, and so on. So there are infinitely many such coefficients, and we want to consider the ideal generated by all those coefficients. So what is the difference between the two examples here? So the difference is that this guy gives us corresponds to CD. So this is projective variety inside a projective space, and this x squared kind of corresponds to a point 0, but non-reduced. So just meaning that x squared is 0 means that x is 0, but the polynomial x does not belong to the ideal generating by x squared. So this is the difference, and actually this question of reducedness will be important for us. We'll get there soon. So this is the examples and the definition of the arc schemes. So any questions so far? So if not, let's go further. So we've defined what are the arc schemes for in general and also in some examples, but we've started with the geometric object with our Veronese curve CD. And now let's try to work with this geometric object instead of working with the ideal defining it. So what do I mean? We have the embedding of the P1 to PD, and given by the homogeneous coordinates here. So these are coordinates of the points in the image. And now let's do a very similar procedure compared to what we've done on the slide before. So we have our A, and instead of considering a single A, let us consider the whole series, A of t. So the recipe is the same as before. So this is the generating function for the variables A0, A1, A2, and so on. And the same thing with the B. So we have our B. And instead of considering a single B, let us consider the whole series. So B0 plus TB1 plus so on. So it's given here. And okay, so as before, let us consider the products of this form. So these are A to D minus 1 of t, and then Bi of t. So you can see that these are infinite series. So this series, so these are series in t with coefficients in the polynomial ring in AI Bj. Okay, so if we expand, so we'll see this in example in a minute, but if we expand, so we get series of polynomials in this polynomial ring, and these are actually the polynomials we are going to be interested in. So let us be more precise. So what is the semi-infinite Veronese curve? So, oops, sorry. So we consider a projective space is given here. So you see, we take our d plus 1 dimensional SL2 representation, V d omega, and then we tensor it with the polynomial ring in one variable. And then, before we had A to d minus I, B to the I, and these were homogeneous coordinates in P, V, d omega. And now each of these guys becomes a series like this. And so meaning that we have not only the I corresponding to this product, but also we have the upper index K. So something like X. So this was the expression for our I. And now we have XIK such that these are exactly the coefficients of the series A to the d minus I of t, Bi of t expanded in t. And these are our coordinates in this infinite dimensional projective space here. And we are interested in the variety corresponding to the points with these coordinates. So let us consider an example, d equals 2. So what do we have? We have x0 of t being a of t squared. So meaning that, for example, x00 is a0 squared, and x01 is a0, a1 twice, etc. And then we have a of t times b of t. So if you expand, you also get infinite number of coefficients, and similar with x2 of t. Okay, so now what is the this is our objects, and what are, oops, So what are the questions we want to ask? So let us first observe that the arc ideal defined above, J infinity of ID, vanishes on the degree D semi-infinite Veronese curve, and this is actually a trivial observation. So you can see, for example, that for D equals 2, so we have such a relation, x0 of t, x2 of t equals to x1 of t squared. And if you substitute the expressions given here, then you obviously get the equality, but there is nothing actually to prove here. It's just because you can consider this a of t as a kind of single quantity and b of t as a single quantity. And then we know that this ID vanishes on the Veronese curve itself. Okay, so, but the questions we want to answer are as follows. Well, we have some problems with navigating the system. Sorry about that. So let me get back. So here we are, and so what are the questions we want to ask? Here are the questions. So first of all, what is the reduced structure of the degree D semi-infinite Veronese curve? So what's the question? The question is as follows. So we can see that J infinity of I D vanishes on our semi-infinite Veronese curve. So we've seen it in the example of D equals 2, but the general case is as obvious as the D equals 2 case. And now we are asking, are there other polynomials satisfying the same property? So we'll get back to this question, but this is similar to the question, to the observation we made before. So if you have an ideal x squared and you consider the vanishing set, the zero set is 1 point. And then there is a polynomial x vanishing here. And we want to ask how much larger the actual vanishing ideal pops up here. So what we have is the J infinity of ID. And so this is the arc ideal of our ID, but the actual vanishing ideal can be larger and actually is larger. And why do we care? Because actually the vanishing ideal, the J infinity of CD, is responsible for the whole semi-infinite Veronese curve. So it somehow defines it, and it canonically corresponds to the geometric object. And in particular, one is interested in the homogeneous coordinate ring. So given here, so this is it. Well, this is a kind of complicated object, but you can see that the picture is somehow similar to the classical situation where we've considered the polynomial ring in the variables x0 up to xd, and then if we take a quotient over the ID, then what we get is something very, very reasonable. So this something very reasonable is actually the direct sum of irreducible representation of SL2. So one should expect that if you consider the reduced ideal here, then one gets something reasonable as well. So if you consider just the arc ideal, so there is no hope getting something nice. But for the reduced ideal, for the ideal of all the polynomials vanishing on our algebraic, on our geometric object on the semi-infinite Veronese curve, one should expect that there is some nice description. And indeed, there is such a description. So let me give some explanation of what happens here. But what I want to say from the very beginning, that this is the right object to study. So I mean, we need the what is called current algebra. So you take the finite dimensional algebra. So G is SL2 so far. But in principle, this is an arbitrary algebra, and then you tensor it with the polynomial ring in one variable, and then you want to somehow describe some representations of this Lie algebra.
Could I just make a quick comment or actually ask a question?
Yes, sure.
So you call it semi-infinite. Is that because you're only looking at positive powers of t?
Absolutely. Yes.
Okay. So in principle, you could look at Laurent polynomials as a...
Yes. Yes.
The second comment is that it's related to my comment earlier that if you look at it from the viewpoint of Grassmannians rather than projective spaces, so Grassmannians of two planes in d dimensions, you just add the t parameter and it becomes just a sort of affinized or polynomialized infinite dimensional analog of the Flickr embedding.
Absolutely. Right. That's true. Actually, this is a very good point. And these infinitized Grassmannians, they really make sense. So, I mean, this is a very nice object. And in general, this is called semi-infinite flag varieties. And these Grassmannians, they are examples. And their structure is also described in terms of the representations of this G tensor C of t of this current algebra. Maybe we'll say something later, but I'm not sure that too much. But indeed, this is a very natural object here. Okay. So before I go into the details for the representation theory of this current algebra, let me show you the answer in the SL2 case. So let me start with d equals 2. So you can see that we have d equals 3, I'm sorry. So we have these three relations. So let me recall that x0 of t is a cubed. x1 of t is a squared of t, b of t, x2 of t is a of t, b squared of t, and x3 of t is b cubed of t. And then, well, one easily sees that these three relations are satisfied. So just plug in and then you get the equality. But there is one very interesting thing, namely that there is this one funny relation which can't be seen on the level of finite dimensional curve, but this is a very simple computation for the, I don't know, the first year calculus, that if you substitute the series given here into this last line, then you get 0. And you see that there are some funny derivatives here. So meaning that there are some strange derivatives, relations with derivatives coming up in this situation in a very natural way. And the claim is that these four relations, they already give the reduced structure. So if you take the coefficients of those four relations, then you get the needed object, the reduced structure. And this is the general form for the general decays. So you can see that there are some, it's not very important the precise form now, but you can see that there are some derivatives popping up here, and the derivatives are well of different orders, but actually the form is more or less the same. So you have the product of the series and their derivatives. So this is the answer, but for SL2, even for SL2, you need representation theory to prove that this is the reduced ideal. So let me say something about the representation.
Evgeny, may I ask a quick question? So
sure, absolutely.
Your ideals are closed under derivative, right?
Right.
Yeah. Okay. Thank you.
That's true. And it's important, actually. It's important, right? Okay. So I'm not sure I want to. Okay, maybe let me say a few words about the general G case just to show you that SL2 is not that kind of special here. So if you have a general simple complex Lie group, then you have looker embedding, so it's given here. So now instead of considering embedding into one single projective space, you need an embedding into the product of projective spaces. For example, for G equals SLR plus 1 and D equals 1, you have the natural classical looker embedding into the projective spaces of Verge powers of the vector representation. And the homogeneous coordinate ring is in a similar way described by this direct sum. So again, this is the classical stuff. And what just I wanted to say that these semi-instant definitions are valid in this general situation. I'm not sure I can get into the general answer in full details, but at least I just assure you that the general G case is also very kind of natural here and also can be worked out. Okay, so let us return to the, just let us describe the representations of the current algebra, which are kind of importance here. So in order to simplify the exposition, I'll stay in type A, although this is not very important. So I mean, the general type case also can be described, but well, some extra care is needed. So in type A, we want to define some modules which are called global Demazure modules, and they are here. So they depend on the parameter D, which is our degree, natural number, and also there is this integral dominant weight lambda, which also enters the indexing set. So we consider the fundamental weights as we did before, and then first we define these modules for fundamental representations. So you can see the definition here. So we do a very, very simple naive thing. So we take, so this is the G of T module. And how is it defined? So you take this G module, which is just the irreducible representation with highest weight D omega I, so fundamental several times, and then you take the polynomial ring in one variable, and since G of T is nothing but G tensor C of T, then Gx on the first factor and Tx on the second factor, and then this is nothing but this kind of very natural module. So you see there is this omega I here, and we want to consider the general lambda, and to this end we consider the more or less standard so-called cyclic product. So what are we doing? So you see these D of D omega I are cyclic representations, meaning that so we have those irreducible modules, and these are highest weight modules. So there is a highest weight vector G, and the whole module is obtained by applying the universal enveloping algebra to this highest weight vector. And also there is this polynomial part, but we also have a polynomial part in our Lie algebra, in our current Lie algebra, and therefore we can somehow get the whole module, the whole global Demazure module, starting from the highest weight vector of this irreducible Vd omega I tensor 1. So now let's get to the definition of this cyclic product. So we have two modules, W1 and W2. And then we have these cyclic vectors, small w1, small w2. We take the tensor product, and then we apply the universal enveloping algebra of the current algebra to this tensor product. And so this is something living inside the tensor product of two initial modules. So this should somehow remind you the situation with the irreducible representations when you have v lambda times v mu being equal to v lambda plus mu. So these are modules, G modules. So this is called the Cartan component inside the tensor product, meaning that if you have two irreducible representations of G and you take two highest weight vectors, you take the tensor product and you apply your universal enveloping algebra, then you get the irreducible module corresponding to the lambda plus mu. Okay, and this somehow makes the next definition very natural. So what we do, we take the Demazure modules corresponding to the fundamental weights. And so we take d omega of t. So just to be precise, so this d, so this is nothing but, let me put a d omega I t is nothing that but v d omega I tensor c of t. And this is what was denoted by d bar d bold d omega I. So we take these modules and we take several modules, the cyclic tensor product of several modules of this sort. For example, if we want to take, so if we consider, say, SL2, and we consider lambda to be 2 omega and any d, then what we get is that d2 omega is d omega, and then cyclic tensor product with d omega. Okay, so we have several these very natural and simple modules, and then we have some operation on them. So yeah, sure.
Why are you calling it as Demazure module? Like, does it have any connections with affine Demazure modules?
Absolutely, right. So I'll get there. So before that, let me give you the relatives of those modules, or rather special cases. So these are the Weyl modules, the global Weyl modules. So namely, if d is 1, then this d lambda, so they are isomorphic to the global Weyl modules. Some of you are experts in this field, but if not, just let me give you very briefly the definition. So these modules are very popular. They introduced and studied by Cherry, Presley, and then Fourier, Littleman, many other people. And so the definition is kind of very concrete. So you consider the Cartan decomposition here. And then the global Weyl module W lambda is defined as a cyclic G of T modules with the following relations. So first of all, one part of the algebra kills it, and then the cartan acts via the weight lambda, and here are standard relations for irreducible representation, so meaning that V lambda sits inside this global Weyl module, and this V lambda is nothing but the universal enveloping algebra of G itself applied to this V. And then the local modules are defined in a very similar way. So the only extra relation is this one. Saying that, so you just kill a part of the Heisenberg algebra, tensor TC of T. So it also acts by 0. So this guy is finite dimensional. And this guy is infinite dimensional. Well, and the structure of these modules, the connection with the previous definition is given by the theorem of Shukato, who says that this cyclic product of W lambda and W mu is nothing but W lambda plus mu. And this somehow illustrates why this is that similar. And now to answer the question on the connection with the affine Demazure modules, so let me explain what's happening for G equals SL2. Maybe I'll get to the general case later, but I'm not sure I have enough time for that. At least I'll state the answer in the SL2 case. So we have lambda being just n omega, because so this is the rank 1 case. And this is the very explicit form of the global Demazure modules we are working with. So you have n times cyclic product of this very simple guy, which is nothing but V d omega tensor C of T. What is the theorem? The theorem says that this global Demazure module admits an action of an algebra, associative algebra, A and omega. So this algebra is nothing but the algebra of symmetric polynomials in n variables. So you see it does not depend on D, but does depend on n. And this action is free and commutes with the SL2 of T action. So it means that if you take the coinvariance, so just the space of generators of these free modules, then you again get the module of the current algebra. And here is the module itself. So, oops, sorry. So this tensoring with the algebra over the trivial module means nothing but taking the quotient. So you take the quotient of D and omega by the algebra A of n omega plus. So this is the algebra of symmetric polynomials with no constant term. Or you can say that you take the space of generators of the free modules, and then this D is, the theorem says that this is the level D affine Demazure module. So this guy. And actually, you can say a lot about this module. For example, the dimension of this module is D plus 1 to the n. You can also compute its character, but at least what's important that this indeed the Demazure module and the level corresponds to the degree of our initial curve. So let's give the geometric theorem for SL2. And you can actually guess that, so we are going to describe the vanishing ideal of this semi-infinite Veronese curve. And the theorem says that the homogeneous coordinate ring is nothing but the direct sum of these global Demazure modules. So you can see that this is very similar to the description of the coordinate ring of the Veronese curve itself, given by V, D, and omega. So actually, one would start here. Well, for SL2 it doesn't matter, but nevertheless. And so you can see that there is a correspondence between those guys. So in some sense, these global Demazure modules, they are nice and natural substitutes for these finite dimensional representations of the algebra itself. And so we can get back to this explicit description of the homogeneous coordinate ring, namely that we have this infinite polynomial ring in infinite number of variables labeled by I from 0 to D and K from 0 to infinity. And this is the ideal, the reduced ideal of all the polynomials vanishing on our curve. And the result is the direct sum over all n of those global Demazure modules. And this n, so this small n, is nothing but the total degree. So I mean, there is a grading on this polynomial ring, degree grading. And so what you somehow consider, you consider the subset, the subspace of polynomials of given degree, and this is exactly what one has on the right hand side. So I'm actually more or less over my time, so maybe let me just say briefly what are we doing in the general G case. So I'm sticking still to the type A case, but nevertheless, there is a notion of affine Demazure modules. And so there is a Demazure modules level 1 and Demazure modules of level D. So if you've been working with these objects, then you know. Otherwise, unfortunately, I don't have time now to give more details. But so there are some natural substitutes to the modules above. And so let me maybe show you the statement. So the so if you want to describe these semi-infinite flag varieties, then you have to work with these global Demazure modules in general. And well, the connection with the affine Demazure modules is the same as in the SL2 case. So there is some algebra acting there, such that the quotient is the local, the natural affine, usual affine Demazure modules, and the algebra is given here. Let me show you. This is the algebra. And then it acts freely, commutes with the G of T action, and the quotient is the affine Demazure module. So probably I'm done, and thank you very much for your attention.
Yeah, thank you. Are there any questions for Evgeny?
I have a question, Evgeny. So these arc spaces of Veronese curve, is there an interpretation or connection with vertex algebras and some vertex algebra representations?
Yes. So so in order to make a connection to the vertex separator algebras, so well, so there are, let me say in the following way. So either you can do something like those small ideals, I mean this baby example with x squared. And then you take the arcs for this x's. So I mean the vertex separator algebra theory, so you also have those fields. Yes, so it means that they are generating functions of something. And then you can consider the relations satisfied by those fields acting somewhere. And then they might be of the form of arc space for something. This is not exactly what's happening for the Veronese curves, but this is really the case in many examples. And if addressing your question, in order to make a link to the vertex separator algebra, one has to consider some object which is called the Belenson-Drinfeld-Grassmannian. So actually, this is kind of complexification of this Veronese curves business. So instead of considering just one Demazure module, you consider how Demazure module expanded to the affine line. So there's no way to describe it in a minute or two. But so the result, this Belenson-Drinfeld-Grassmannian can be the line bundles, and the section of the line bundles, they can be described in terms of this global Demazure module. So this is the situation, and this is actually the topic of our paper with Ilya Dumanski and Finkelberg. But so we are not discussing these connections, vertex separator algebras there, but nevertheless, this is the approach.
So your global Demazure modules do have some sort of interpretation in terms of Schubert varieties or some
right.
new arc version of Schubert varieties.
No, yes, so they have interpretation in terms of Schubert varieties, but these are Schubert varieties in the Belenson-Drinfeld-Grassmannian.
I see.
So these are somehow kind of global version of the Belenson of the Schubert variety. So you actually all know that what's connection between the affine Schubert varieties and affine Demazure modules, that there are, or even without affine. So there are line bundles on Schubert varieties, and the sections, the dual sections of these line bundles, they are isomorphic to the Demazure modules.
Right.
And in order to get the global Demazure modules, you consider the global version of the Schubert varieties, and these are Schubert varieties inside the Belenson-Drinfeld-Grassmannians. These are kind of global version of the Grassmannians, of the affine Grassmannians.
So is it easy to write down presentation for these global Demazure modules?
Say it again?
Generators and relations.
This is a very good question. I don't know such a presentation. We're trying to find it, but we are not able so far. But this is a very good question.
Could I just interject? This might be just equivalent to the comment that Michael made about Schubert varieties and also the Belenson-Grassmannian. But again, looking at things from the viewpoint of a Grassmannian extended with its polynomials in one variable, there's, the exterior space in which the Plucker embedding is made is the space of holomorphic sections of the dual determinantal line bundle over the Grassmannian. And that brings in the Borel-Weyl-Bott theory. So I'm just wondering if that's somehow equivalent to these Mazur modules that you were talking about, or the Belenson-Grassmannian.
So yes, this is absolutely right. So this is the main theorem of our paper with Ilya Dumanski and Misha Finkelberg, that if you consider the Schubert varieties inside the Belenson-Drinfeld-Grassmannian, Then there is a line bundle, which is an analog. It's just called the determinantal line bundle, and the sections of this line bundle on the Schubert varieties, of these global Schubert varieties, they produce the global Demazure modules. That's right.
Okay. Are there other questions? I had one other question. You said as an aside that if we don't reduce and we take the original the original coordinate well, kind of coordinate ring, yes. we won't get interesting module structure for current algebra. I imagine it's got to be enormous because your global Weyl modules are already big. But do you have any idea of what would happen or any reason why this is really completely uninteresting?
No, I'm not saying this is not interesting, but I'm probably this is also this is an interesting question. But what I wanted to say that I don't understand how one can describe it, because if you consider the reduced structure, then this homogeneous part, for example, of degree n, is a cyclic module over the current algebra. Right. If you consider a non-reduced ideal, just the arc ideal, then the result is a larger module, and it's not going to be a cyclic module. So probably there is some structure there, maybe so it has a filtration by cyclic modules or some of this sort. I'm not saying that it's not an interesting question. It's also a natural question, but I just don't know how one can work with this object and what are the kind of tools we can use to describe it.
Any other questions? Okay, let's thank Evgeny again.
Thank you.